Hello there. I'm so glad you found your way here tonight. Right now, as you settle in, imagine for a moment that our universe is not alone. That beyond the faint glow of distant galaxies, past the edge of everything we can observe, there may be others. Not just one or two, but perhaps an infinite ocean of universes, each with its own stars, its own laws, its own stories. Some scientists picture bubbles of reality drifting in an endless cosmic sea. Others see branching timelines where every possibility unfolds. There are theories where black holes give birth to entirely new worlds, and others where hidden dimensions hold realities we can never touch. Tonight, we journey into the quiet wonder of the multiverse. We will explore over 100 soothing facts about parallel universes, cosmic possibilities, and the strange beauty of infinite realities waiting beyond our own. There is no test at the end, no rush, no urgency, just the gentle unfolding of one of the most mind-expanding ideas in all of science to carry you softly towards sleep. So let your breathing slow, let your thoughts grow quiet, and allow yourself to drift into the peaceful vastness of the multiverse. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable possibilities that may lie beyond our universe. Either way, this space is for you. There is something deeply calming about contemplating the vastness of many worlds. Every bubble universe, every parallel branch, every hidden dimension carries within it a story we may never fully know. You are part of that story. Somewhere in the infinite expanse, if the theories are true, there may be other versions of you living lives both similar and unimaginably different. The very atoms that make up your body were forged in stars, and those same elements may exist in countless other realities. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in, let the weight of the day drift away, and let us begin with the first of many quiet truths about the multiverse. The multiverse is patient beyond measure. Its theories have been developing for decades. Its implications stretch across philosophy, physics, and imagination itself. And yet, within all that vastness, there are sudden bursts of wonder. Ideas that suggest our universe is just one among countless others. Visions of reality that expand far beyond what we can ever directly observe. Tonight, we will wander through this magnificent conceptual landscape. We will meet the theories that predict parallel worlds. We will discover the strange possibilities that different universes might hold. And we will uncover truths about the multiverse that may surprise even the most curious minds. But there is no hurry. The multiverse, if it exists, has been there since the beginning of time. It can continue its quiet existence while you rest. Let us begin with what the multiverse truly means. The multiverse is the idea that our universe may be just one among countless others. The word multiverse refers to the breathtaking possibility that the cosmos we observe, with all its billions of galaxies and trillions of stars, is only a single pocket of reality among a vast or even infinite collection of separate universes. In this picture, what we call the universe is merely one chamber in a much grander structure, each chamber potentially operating under its own set of physical rules. The concept is not the invention of science fiction writers, though it has certainly inspired them. It arises naturally from several well-established branches of theoretical physics, including quantum mechanics, inflationary cosmology, and string theory. Each of these frameworks, when pushed to its logical conclusions, suggests that our universe need not be unique. The multiverse idea challenges one of our most deeply held assumptions, that there is only one reality, and it does so using the same mathematics that has been tested and confirmed in terrestrial laboratories. Whether the multiverse is ultimately real or forever beyond our reach remains one of the most compelling open questions in modern science. Some physicists believe the multiverse is an unavoidable consequence of our best theories. The multiverse is not an idea that physicists went looking for. It emerged unbidden from the mathematics of theories that were designed to explain phenomena we can actually observe. Inflationary cosmology, which was developed to explain the remarkable uniformity of the cosmic microwave background, predicts that once inflation begins, it tends to continue forever in most regions of space, spawning an endless number of separate bubble universes. String theory, constructed to unify gravity with the other forces, generates a landscape of possible vacuum states so vast that each one could correspond to a different universe with different physical constants. Quantum mechanics, in the many worlds interpretation, implies that every measurement causes the universe to branch into multiple copies. In each of these cases, the multiverse is not an optional add-on, but a direct consequence of the theory's internal logic. Many physicists find this deeply compelling. If our best and most successful theories all point towards the same conclusion, perhaps the multiverse deserves to be taken seriously rather than dismissed as speculation. The many worlds interpretation suggests that every quantum event branches into parallel realities. In standard quantum mechanics, a particle can exist in a superposition of many states at once, but the moment it is measured, only one outcome is observed. The puzzle of what happens to all the other possibilities has haunted physics since the theory was first developed. The many worlds interpretation, first proposed by Hugh Everett in 1957, offers a radical answer. It says that nothing is discarded. Instead of a single outcome being selected and the rest vanishing, all outcomes occur, each in its own separate branch of reality. Every time a quantum event takes place, the universe quietly splits, and each branch continues to evolve independently. You experience only one branch, which is why you see a single result, but the other branches are equally real. The implications are staggering. Every quantum interaction that has ever taken place, in every atom, on every star, throughout all of cosmic history, has generated a new fork in the tree of reality, creating a structure of unimaginable complexity. In this view, every decision you have ever made still exists somewhere in another branch. If the many worlds interpretation is correct, then the choices that define your life, the paths you took, and the ones you did not, all continue to exist in other branches of reality. The version of you that turned left instead of right, the one that chose a different career, the one who stayed a little longer in a particular moment, all of them are out there, living their own complete lives in their own complete universes. These branches are not ghostly or incomplete. They are as fully realized as the branch you inhabit now, each with its own history, its own future, and its own version of every person you have ever known. The branching is not something that happens only at moments of human decision. It occurs at every quantum event, from the decay of an atom to the scattering of a photon. Human choices are embedded within this vast and continuous process of branching. The many worlds picture turns every moment of uncertainty into a celebration of possibility, a reminder that the story of reality is far larger than any single life can contain. String theory predicts as many as 10 to the 500 possible universes. String theory requires extra dimensions of space beyond the 3 we can see, and these extra dimensions can be curled up into tiny shapes called Calabi-Yau manifolds. The precise shape of the hidden dimensions determines the fundamental constants of the universe that forms around them, including the masses of particles, the strengths of forces, and even the number of generations of matter. Because there is an extraordinary number of possible shapes, each producing a different set of physical laws, string theory generates an almost inconceivably vast collection of possible universes. Current estimates put this number at roughly 10 to the power of 500, a figure so large that it dwarfs the number of atoms in the observable universe by hundreds of orders of magnitude. Each of these possible universes represents a different valley in what physicists call the string landscape, a terrain of possibilities where the laws of nature vary from peak to peak. Our universe, with its particular constants and particles, would be just one valley among this immense multitude. This vast number of possibilities is known as the string landscape. The string landscape is a metaphorical terrain in which each point represents a different possible set of physical laws and constants. Imagine a mountainous region stretching in every direction, with valleys of every depth and ridges of every height. Each valley corresponds to a stable or metastable vacuum of string theory, and a universe sitting in that valley would experience the particular physical constants associated with it. The landscape was first clearly described in the early 2000s, when physicists realized that the mechanisms for stabilizing the extra dimensions of string theory could produce an astronomically large number of distinct vacua. This discovery was both exciting and unsettling. On one hand, it made it plausible that at least one vacuum matches our universe. On the other, it seemed to undermine the hope that string theory would uniquely predict the laws of nature. The landscape has become one of the most debated concepts in modern theoretical physics, raising profound questions about predictability, uniqueness, and the role of the observer in determining which laws we experience. Some scientists picture the multiverse as an ocean of bubbles, each one its own cosmos. One of the most evocative images of the multiverse is the bubble universe picture, which emerges from the theory of eternal inflation. In this scenario, the vast majority of space is inflating at a tremendous rate, stretching faster than light and filling itself with energy. Occasionally, a small region of this inflating space undergoes a phase transition, settling into a lower energy state and forming a bubble. Inside the bubble, inflation ends and a more familiar kind of universe develops, with particles, forces, and eventually galaxies and stars. But outside the bubble, inflation continues and new bubbles are constantly forming. Each bubble is effectively a separate universe, cut off from the others by the endlessly expanding space between them. The bubbles float in an infinite sea of inflating space, like soap bubbles drifting through the air, each one carrying an entire cosmos within its walls. This picture is not merely poetic. It follows directly from the equations of inflationary cosmology, and many physicists regard it as one of the most natural predictions of the theory. Each bubble universe may have its own unique laws of physics. When a bubble universe nucleates within the inflating background, the phase transition that creates it can select a particular vacuum from the string landscape. This means that the physical constants inside the bubble, the masses of particles, the strengths of the fundamental forces, and even the number of spatial dimensions may differ from those in our own universe. In one bubble, gravity might be slightly stronger, causing stars to burn through their fuel more quickly. In another, the electromagnetic force might be weaker, altering the structure of atoms and making chemistry as we know it impossible. The laws of physics that we have measured so carefully in our laboratories may be local features of our particular bubble rather than universal truths. This idea is both humbling and liberating. It suggests that the specific numbers that appear in our equations of physics are not uniquely determined by some deep mathematical principle, but are instead the result of a cosmic lottery, selected from an enormous menu of possibilities by the random process of bubble nucleation. Eternal inflation suggests that new universes are constantly being created. Eternal inflation is a consequence of the physics of the inflationary epoch, the brief period of extraordinary expansion that is believed to have occurred in the first fraction of a second after the Big Bang. In most models of inflation, the inflating region of space expands so rapidly that even as some parts of it settle down into bubble universes, the remaining inflating space grows faster than it is consumed. This means that inflation never ends globally. It continues forever in the bulk of space, perpetually spawning new bubbles, each of which becomes a separate universe with its own Big Bang, its own cooling phase, and its own potential for stars, planets, and life. The process has no beginning and no end. It is a self-sustaining engine of cosmic creation, powered by the energy of the inflating vacuum. Each new bubble is born independently, with no memory of the bubbles that came before. The result is an ever-growing collection of universes, a multiverse that expands not only in space, but in the sheer number of realities it contains. Even as you rest tonight, new universes may be budding somewhere beyond our reach. If eternal inflation is correct, then the birth of new universes is not a rare or ancient event, but an ongoing process that continues at this very moment. While you lie here listening, the inflating regions of the multiverse are stretching and spawning new bubbles, each one blossoming into a fresh cosmos with its own particular set of physical laws. These new universes are forever beyond our ability to observe or contact, separated from us by the impossibly rapid expansion of the inflating space between bubbles. No telescope will ever see them, no signal will ever reach them, and no traveler will ever cross the gap. Yet the mathematics of inflation suggests that they are there, as real as our own universe, quietly coming into existence in the vast reaches beyond our cosmic horizon. There is something deeply peaceful about this idea, that the act of creation is not finished, that the cosmos is still fertile and still generating new worlds, even as the familiar stars above us shine in their ancient patterns. In an infinite cosmos, every possible arrangement of matter must eventually occur. If the universe is spatially infinite, and the amount of matter and energy in any given region is finite, then the laws of probability lead to a startling conclusion. Every possible configuration of matter, no matter how unlikely, must be realized somewhere. This is because there are only a finite number of ways to arrange particles within any region of a given size, but an infinite number of such regions spread across the endless expanse of space. Eventually, every arrangement that is physically permitted will occur, not just once, but an infinite number of times. This means that somewhere unimaginably far away, there is a region of space that is an exact copy of our own observable universe, atom for atom, star for star. The distance to such a duplicate is fantastically large, far exceeding the observable universe, but in an infinite cosmos, distance is no obstacle. This idea, sometimes called the Level 1 multiverse, does not require any exotic physics beyond the assumption that space goes on forever, an assumption that is consistent with current observations. Somewhere unimaginably far away, there could be another planet exactly like Earth. If the universe is infinite, then the mathematics of probability guarantees that every possible arrangement of atoms will eventually repeat. Somewhere, at a distance so vast that light would take far longer than the age of the universe to travel there, there could exist another planet with the same oceans, the same continents, and the same delicate atmosphere as Earth. The chemistry would be identical, the geology would mirror our own, and the sunlight streaming through its sky would feel indistinguishable from a morning here at home. This duplicate Earth would not be a mystical or supernatural place. It would be a straightforward consequence of infinite space and finite possibilities. The particles there would obey the same laws of physics as ours, and they would have assembled themselves into the same structures simply because, given infinite room, even the most improbable arrangement must occur. The thought is both dizzying and oddly comforting. In the boundless reach of an infinite cosmos, our world, precious as it is, may not be alone. On that Earth, someone who looks exactly like you may be living a nearly identical life. If an exact copy of our planet exists somewhere in an infinite universe, then it follows that an exact copy of you exists there as well. This is not a matter of belief or speculation, but a consequence of the mathematics of infinity. Given enough space, the particular arrangement of atoms that makes up your body, your brain, your memories, and your personality must recur. That other version of you would be waking up in the same kind of room, thinking the same kinds of thoughts, and going about a day that is indistinguishable from your own. The two of you would never know about each other, separated by a distance so large that no signal could ever bridge it. Yet you would both be equally real, both products of the same laws of physics playing out in the same way. This idea stretches the imagination to its limits, but it is a straightforward prediction of an infinite cosmos. It suggests that individuality, the sense that you are one of a kind, may be a local truth rather than a cosmic one. A little farther still, there might be a version of you whose life took a different turn. Beyond the hypothetical copy of Earth where everything is identical, there would be other copies where things differ in small but meaningful ways. Perhaps in one of these versions, you chose a different path at a critical moment in your life, and that single divergence led to a cascade of different experiences, relationships, and opportunities. The physics that governs these distant regions is the same as ours, but the particular sequence of events that shapes a life can vary enormously even with the tiniest change in initial conditions. In an infinite universe, every possible variation of your personal history would be played out somewhere, from lives that are almost identical to yours to lives that are unrecognizably different. Some versions might be happier, others more difficult, and still others might exist in circumstances you have never imagined. The idea is humbling, suggesting that the life you are living right now is just one thread in an unimaginably vast tapestry of possibility, each thread as real and as vivid as your own. Quantum mechanics allows particles to exist in multiple states until observed. At the heart of quantum mechanics lies a deeply strange feature. A particle does not possess a definite property until that property is measured. Before measurement, the particle exists in a superposition, a ghostly blend of all the states it could possibly occupy. An electron, for example, does not have a definite position before you look for it. Instead, it is described by a wave function that assigns a probability to each possible location. When you perform a measurement, the wave function appears to collapse, and the particle is found in one particular state. What happened to all the other possibilities? This question, known as the measurement problem, has been debated since the earliest days of quantum theory. In the standard Copenhagen interpretation, the other possibilities simply vanish. But other interpretations, most notably the many worlds interpretation, suggest that they do not vanish at all. Every possible outcome is realized in a separate branch of reality, making the quantum world far richer and more populated than it appears from any single vantage point. Hugh Everett proposed that instead of choosing one outcome, the universe splits. In 1957, a young physicist named Hugh Everett put forward one of the boldest ideas in the history of science. He suggested that when a quantum measurement is performed, The universe does not select a single outcome and discard the rest. Instead, the universe splits into as many copies as there are possible results, and each copy contains a version of the observer who sees one particular outcome. In Everett's picture, there is no wave function collapse, no mysterious moment when possibilities are reduced to a single reality. Everything that can happen does happen, each in its own branch. The idea was initially met with skepticism and even ridicule, and it took decades for the physics community to give it serious attention. Today, the many worlds interpretation has a significant following among physicists and philosophers, though it remains far from universally accepted. Everett himself left physics shortly after publishing his thesis, but his idea has outlived him, growing in influence and inspiring generations of scientists to take the reality of parallel universes seriously. Every quantum event becomes a fork in the road, and the cosmos takes all paths. In the many worlds interpretation, the branching of reality is not limited to dramatic events or conscious decisions. It occurs at every quantum interaction, no matter how small or how fast. Every time an atom absorbs or emits a photon, every time a radioactive nucleus decays, every time two particles scatter off each other, the universe forks. The number of branchings that have occurred since the beginning of time is beyond calculation, a number so vast that it has no meaningful analogy in everyday experience. Each branch evolves independently, carrying forward its own version of the entire cosmos. From within any single branch, everything appears perfectly normal and self-consistent. There is no sign of the other branches, no ghostly echo of roads not taken. The branching is silent, seamless, and utterly democratic, giving every possible outcome an equal claim to reality. The image is both beautiful and overwhelming. The cosmos as an endlessly branching tree, its limbs stretching in every conceivable direction, each one as solid and as real as the trunk from which it grew. You will never meet your other selves, but in the multiverse, they may be as real as you. One of the most poignant aspects of the many worlds interpretation is that the different branches of reality are entirely isolated from each other. Once a branching has occurred, the two resulting universes evolve independently, and there is no known mechanism by which information or matter could pass between them. This means that even if countless versions of you exist in parallel branches, you can never communicate with them, observe them, or confirm their existence. Each version of you is as alone in their branch as you are in yours. Yet the mathematics of quantum mechanics treats all branches on an equal footing. None is more real or more fundamental than any other. If the theory is correct, then your other selves are not hypothetical or imaginary. They are as fully real as you are, living complete lives in complete universes, experiencing joys and sorrows that you will never learn about. The separation is absolute, but the existence, if the theory holds, is genuine. Bubble universes might collide, leaving scars across the cosmic microwave background. In the bubble multiverse of eternal inflation, each universe is a separate bubble floating in an endlessly expanding sea of inflating space. Most bubbles are carried apart by the expansion faster than they can approach each other, but occasionally two bubbles may nucleate close enough together to collide. Such a collision would be a cataclysmic event, releasing enormous energy at the point of contact and potentially leaving an observable mark on the interior of each bubble. For our universe, the most promising place to look for such a mark is the cosmic microwave background, the faint afterglow of the Big Bang that fills the sky in every direction. A bubble collision would produce a distinctive circular pattern of slightly warmer or cooler temperature, a cosmic bruise etched into the oldest light in the universe. Cosmologists have searched for such patterns using data from satellite missions, and while no convincing detection has been made, the search continues. The discovery of a bubble collision signature would be among the most extraordinary findings in the history of science, providing direct evidence for the existence of other universes. Scientists have searched for such patterns in the ancient radiation from the Big Bang. The cosmic microwave background radiation is a snapshot of the universe as it existed roughly 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form and light to travel freely for the first time. This ancient radiation has been mapped with extraordinary precision by satellite observatories, revealing tiny fluctuations in temperature that encode information about the earliest moments of cosmic history. If a bubble collision had occurred in our past, its imprint would appear as a distinctive disc-shaped anomaly in the temperature map, with a characteristic pattern of concentric rings. Several research groups have analyzed the data looking for such features, using sophisticated statistical methods to distinguish a genuine collision signal from the random fluctuations that naturally occur in the background. So far, no statistically significant detection has been reported, though some intriguing candidate features have been identified. The sensitivity of the instruments continues to improve, and future missions may be able to probe smaller and subtler signals, keeping alive the hope that the first direct evidence of another universe might one day be found. Some theories suggest our own universe was born inside a black hole in another cosmos. One of the most imaginative proposals in cosmology is the idea that the Big Bang was not the absolute beginning of everything, but rather a transition from a pre-existing universe, occurring deep within the interior of a black hole. When a massive star collapses under its own gravity and forms a black hole, the matter at its core is crushed to extraordinary densities. In general relativity, this collapse leads to a singularity, a point of infinite density where the equations break down. But some physicists have proposed that quantum gravitational effects might prevent the singularity from forming, causing the collapsing matter to bounce and expand into a new region of space-time that is causally disconnected from the original universe. This new region would appear, from the inside, as an expanding universe with its own Big Bang. The idea neatly resolves several puzzles about the initial conditions of our universe and suggests a deeply generative cosmos in which every black hole may be the seed of a new reality. At the core of a collapsing star, the equations hint at a rebound into a new space. When a star far more massive than our Sun exhausts its nuclear fuel, it collapses inward with devastating force. The core falls at a significant fraction of the speed of light, and the temperatures and pressures soar beyond anything found elsewhere in the universe. In classical general relativity, this collapse leads inexorably to a singularity, a point where density becomes infinite and the known laws of physics cease to make sense. However, several approaches to quantum gravity suggest that the singularity may be avoided. Instead of collapsing to a point, the matter at the core may reach a maximum density and then bounce, expanding outward into a new region of space-time that is disconnected from the parent universe. This quantum bounce would be the Big Bang of a new cosmos, seeded by the matter and energy of the collapsing star. The new universe would inherit certain properties from its parent, potentially passing on information about the laws of physics that favored its creation. It is a remarkable vision, death and birth intertwined at the heart of the most violent events in the cosmos. Every black hole in our skies could be a nursery for worlds we will never see. If the hypothesis that universes are born inside black holes is correct, then the implications are staggering. Our own observable universe contains billions of stellar mass black holes and supermassive black holes at the centers of galaxies, each one potentially harboring a new cosmos in its interior. we would never be able to observe these child universes directly because the event horizon of each black hole prevents any information from reaching us. But the sheer number of black holes in our universe would make it an extraordinarily fertile cosmic parent, giving birth to countless new realities through the relentless process of stellar collapse. Each child universe might in turn contain its own black holes, which would spawn still more universes, creating an endlessly branching tree of cosmic generations. This picture is sometimes called cosmological natural selection, a term coined by physicist Lee Smolin, who proposed that universes which produce more black holes are more successful at reproducing, and therefore come to dominate the multiverse population. The multiverse would not just be vast, but endlessly generative. What makes the multiverse so captivating is not merely its size, but its relentless creativity. Whether through the eternal inflation of bubble universes, the quantum branching of the many worlds interpretation, or the birth of new cosmoses inside black holes, the multiverse is a structure that never stops producing new realities. It is not a static collection of pre-existing worlds, but a dynamic, ever-growing entity that creates new universes as naturally as a tree produces leaves. Each mechanism of universe creation operates independently and continuously, meaning that the total number of universes is not fixed, but is always increasing. This generative quality gives the multiverse a character quite unlike anything in our everyday experience. It is not a container with a set number of objects inside it. It is a process, an ongoing act of cosmic creation that has no end point and possibly no beginning. The multiverse, if it exists, is the most fertile and prolific entity conceivable, endlessly exploring the space of physical possibility. According to brain cosmology, our universe may be floating in higher dimensional space. Brain cosmology is a framework inspired by string theory and M-theory, in which our visible universe is a three-dimensional membrane, or brain, embedded in a higher dimensional space known as the bulk. In this picture, the particles and forces we are made of, everything from quarks to photons, are confined to the surface of the brain and cannot escape into the extra dimensions. Only gravity can propagate freely through the bulk, which is why it appears so much weaker than the other fundamental forces. The bulk itself may be vast, possibly infinite, and may contain other brains drifting in parallel to our own, each one carrying its own version of a universe. The idea is startling in its implications. Our entire observable cosmos, with all its galaxies and clusters and cosmic voids, may be just a thin membrane floating in a much larger space that we can never directly perceive. Brain cosmology provides a natural setting for the multiverse, with each brain representing a separate universe and the bulk serving as the arena in which they coexist. Other brains might drift nearby, each carrying its own universe with different laws. In the higher dimensional bulk of brain cosmology, multiple brains can exist simultaneously, separated by distances in the extra dimensions that may be as small as a fraction of a millimeter. Each brain is a self-contained universe, and the physical laws on each brain are determined by its own properties and its position within the bulk. Two brains that are located at different points in the extra-dimensional space might experience different strengths of the fundamental forces, different particle masses, or even different numbers of spatial dimensions within the brain. The inhabitants of each brain, if any exist, would perceive their own brain as the entire universe, unaware of the parallel worlds floating nearby in the bulk. Gravity, being the one force that can leak between brains, might provide the only bridge between these separate realities. Some physicists have speculated that the gravitational influence of a nearby brain could explain subtle anomalies in our own universe, though no such evidence has been conclusively identified. The picture of parallel brains drifting through a higher dimensional void is one of the most dramatic and visually striking ideas to emerge from modern theoretical physics. When two brains collide, they may release unimaginable energy and create a new Big Bang. In brain cosmology, the collision of two brains is one of the most cataclysmic events conceivable. When two membranes moving through the bulk meet and touch, the kinetic energy of their approach is converted into a tremendous burst of radiation and matter, heating the surfaces of the brains to extraordinary temperatures and setting off a period of rapid expansion. This process bears a striking resemblance to the Big Bang, and some physicists have proposed that our own Big Bang may have been triggered by just such a collision. The ekpyrotic model, named after the ancient Stoic concept of a world consumed by fire and reborn, describes a scenario in which two initially cold and empty brains drift towards each other, collide, and produce the hot, dense, expanding universe we observe today. The appeal of this model is that it provides a physical mechanism for the Big Bang rather than simply postulating it as an initial condition. It also suggests that brain collisions may have happened before and may happen again, raising the possibility of a cyclic cosmos that endlessly renews itself. Our own Big Bang might have been the result of a collision between cosmic membranes. The ekpyrotic scenario and its cyclic extension propose that the Big Bang was not the absolute beginning of time, but the latest in a potentially endless series of brain collisions. In this picture, two parallel brains undergo periodic cycles of approach, collision, expansion, cooling, and eventual return, each collision producing a new Big Bang and each cycle lasting trillions of years. The universe we observe today is in the expansion phase of the current cycle, and the galaxies we see around us are the products of the most recent collision. When the brains eventually separate, the universe cools and empties, only for the brains to be drawn together again by forces operating in the extra-dimensional bulk. The next collision will produce a new burst of energy, a new expansion, and a new generation of stars and galaxies. This cyclic model eliminates the need for a singular beginning, replacing it with an eternal process that has no first moment and no final end. It is a profoundly different picture of cosmic history from the standard Big Bang model, and while it remains speculative, it is grounded in the mathematics of string theory and brain dynamics. The laws of physics themselves may change from universe to universe. One of the most unsettling implications of the multiverse is that the physical laws we have spent centuries discovering may not be universal at all. In our universe, the speed of light, the charge of the electron, the strength of gravity, and the masses of the fundamental particles all take specific numerical values that have been measured with extraordinary precision. We tend to think of these as fixed properties of nature, carved into the fabric of reality itself. But in the multiverse picture, these values are accidents, determined by the particular vacuum state or compactification geometry of each individual universe. In another universe, the electron might be heavier, gravity might be stronger, or there might be additional forces we have never encountered. The laws of physics as we know them would be local bylaws, valid within our bubble, but not beyond it. This idea fundamentally changes the nature of the quest for the laws of nature, transforming it from a search for absolute truth into an exploration of what is possible within a landscape of physical variation. In some universes, gravity might be weaker or stronger than in ours. Gravity is the weakest of the four known fundamental forces, and yet it shapes the largest structures in the cosmos. It holds planets in orbit, binds galaxies together, and governs the expansion of the universe itself. In our universe, the strength of gravity is described by Newton's gravitational constant, a number that has been measured with great care. But in the multiverse, this constant need not take the same value everywhere. In a universe where gravity is significantly stronger, stars would form more readily, but would also burn through their fuel far more quickly, leaving less time for complexity to develop. Planets would be smaller and denser, and the escape velocity needed to leave their surface would be much higher. In a universe where gravity is much weaker, clouds of gas might never collapse into stars at all, leaving the cosmos cold and dark. The particular strength of gravity in our universe appears to be finely balanced, strong enough to form stars and galaxies, but gentle enough to allow them to persist for billions of years. A slight change in the charge of the electron could unravel atoms as we know them. The electron carries a tiny negative electrical charge that is precisely balanced by the positive charge of the proton. This balance is what makes atoms electrically neutral, allowing them to form the stable structures that underpin all of chemistry and biology. If the charge of the electron were even slightly different, the consequences would be catastrophic. A small increase might cause electrons to be bound too tightly to their nuclei, preventing the formation of chemical bonds. A small decrease might make atoms unstable, unable to hold together under the electromagnetic forces that govern their behavior. In either case, the rich chemistry that makes life possible in our universe would not exist. The periodic table as we know it, with its elegant structure and its capacity for complexity, depends on the precise value of the electron charge. In the multiverse, universes with slightly different values of this charge would be profoundly different places, most of them far less hospitable to the kind of structured matter that gives rise to stars, planets, and living things. The constants we observe may be the markers of our particular valley in the landscape. In the string landscape, each vacuum corresponds to a particular set of physical constants, and our universe occupies one specific valley among an enormous number of alternatives. The values we measure for the speed of light, the gravitational constant, the mass of the Higgs boson, and dozens of other parameters are not determined by any known fundamental principle. They are simply the values that happen to characterize the vacuum in which we find ourselves. This realization has profound implications for the way we think about the laws of nature. Rather than being universal truths, our physical constants may be geographical facts, describing the local features of our particular region of the landscape. Just as the climate and terrain vary from one valley to another on Earth, the fundamental constants vary from one vacuum to another in the string landscape. The constants feel fundamental to us because we have no way of accessing another vacuum, but from the perspective of the landscape, they are as contingent and parochial as the color of the local soil. Some universes might exist with more than 3 dimensions of space. We experience 3 dimensions of space, up and down, left and right, forward and backward, and this seems so natural that it is easy to assume it must be universal. But the multiverse allows for the possibility that other universes might have a different number of spatial dimensions altogether. String theory, which requires 9 or 10 spatial dimensions for mathematical consistency, suggests that extra dimensions are not only possible, but expected. In our universe, the additional dimensions are thought to be curled up so tightly that they are invisible at everyday scales. But in other universes, some or all of the extra dimensions might be large and accessible, creating a spatial experience that is radically different from our own. A being in a 4-dimensional space would have an additional direction of movement that we simply cannot imagine, much as a creature confined to a flat surface cannot conceive of height. The geometry, the physics, and the very nature of objects would be different in such a universe, opening up possibilities that are entirely beyond our 3-dimensional intuition. String theory works best with 10 or 11 dimensions, most curled up too small to see. One of the most striking features of string theory is its demand for extra spatial dimensions. The mathematics of vibrating strings is only consistent in a spacetime with 10 dimensions, and M-theory extends this to 11. Since we only perceive 4 dimensions, 3 of space and 1 of time, the remaining dimensions must be hidden somehow. The most widely accepted explanation is that these extra dimensions are compactified, curled up into shapes so small that they are far below the resolution of any experiment we can currently perform. The size of these hidden dimensions is typically around the Planck length, roughly 10 to the power of minus 35 meters, a scale at which our ordinary notions of space and geometry break down. Despite being invisible, the extra dimensions play a crucial role in determining the physics of the visible world. The way they are folded and twisted determines which particles exist, how strong the forces are, and what the fundamental constants of nature will be. Every different compactification produces a different universe, contributing to the enormous diversity of the string landscape. In other universes, extra dimensions might not be hidden at all. While in our universe, the extra dimensions predicted by string theory are thought to be compactified to unimaginably small scales, there is no fundamental reason why this must be the case in every universe across the multiverse. In some regions of the string landscape, the compactification might not occur, or the extra dimensions might stabilize at a much larger size, becoming fully accessible features of the physical world. A universe with large extra dimensions would be profoundly different from our own. The strength of gravity, which in our universe is diluted because it can spread into the compact extra dimensions, might behave very differently there. The inverse square law that governs how gravitational force falls off with distance would be replaced by a different power law, reflecting the higher dimensional geometry. The very structure of matter, the way particles interact, and the way objects move would be altered in ways that are difficult to imagine from our three-dimensional perspective. Such universes would be genuinely alien, operating under a geometry that has no analog in our experience. Beings in a higher dimensional universe would see our three-dimensional space as strangely flat. If intelligent beings could exist in a universe with more than 3 spatial dimensions, their perception of reality would be vastly richer than ours. They would have additional directions of movement, additional axes along which to build structures, and a sense of spatial depth that we simply cannot access. From their perspective, our three-dimensional universe would appear as a thin, flat slice of a much larger space, much as a two-dimensional sheet of paper appears flat and featureless to us. They would be able to see inside three-dimensional objects in the same way that we can look inside a two-dimensional drawing, peering into structures that are opaque from our limited vantage point. The analogy of Flatland, a famous thought experiment about beings confined to a two-dimensional world, captures the idea well. Just as Flatlanders cannot imagine height, we cannot truly imagine the fourth spatial dimension. And just as we can look down upon Flatland and see everything at once, a higher dimensional being could perceive our entire universe laid bare. Some universes might have no stars at all, only endless darkness. Stars are the engines of light and complexity in our universe, but their existence depends on a delicate balance of physical constants. The strength of gravity must be great enough to compress clouds of hydrogen gas until nuclear fusion ignites, while the nuclear forces must be strong enough to sustain the fusion reactions that power the star. If any of these constants were significantly different, stars might never form. In a universe where gravity is too weak, gas clouds would never collapse. In a universe where the nuclear force is too feeble, hydrogen atoms would not fuse into helium. Without stars, there would be no light, no heavy elements forged in stellar cores, and no planets on which complexity could develop. The universe would be a vast, dark expanse of drifting gas and particles, cold and silent beyond imagining. In the multiverse, such starless universes may be far more common than universes like ours, where the constants happen to fall within the narrow range that allows stars to shine. Without the familiar scaffolding of light, matter would drift forever in cold silence. In a universe without stars, the story of matter would be very different from the one we know. There would be no sources of energy to warm the clouds of gas that fill intergalactic space. Without energy, chemical reactions would slow to a halt, and the complex processes that build molecules and minerals would never occur. Matter would remain in its simplest forms, atomic hydrogen, and perhaps some helium left over from the initial moments of that universe's own version of the Big Bang. These atoms would drift through the void in vast, diffuse clouds, growing colder with each passing eon as the universe expanded and the temperature dropped ever closer to absolute zero. There would be no planets, no oceans, no atmospheres, and no possibility of the intricate chemistry that gives rise to life. The universe would be a place of ultimate stillness, a cosmic desert stretching in every direction with nothing to break the silence. It is a picture that highlights just how extraordinary our own universe is, with its blazing stars and its vibrant chemistry. Quantum fluctuations could be spawning whole new universes right now. Quantum mechanics tells us that even the emptiest regions of space are not truly empty. The vacuum seethes with fleeting disturbances known as quantum fluctuations, momentary surges of energy that pop into existence and vanish almost instantly. In everyday physics, these fluctuations are tiny and short-lived, but in certain extreme conditions, such as those that might prevail in the inflating regions of the multiverse, a quantum fluctuation could grow large enough to seed an entirely new universe. The energy of the fluctuation would trigger a burst of inflation, stretching a microscopic region of space into a vast, self-contained cosmos. This process does not violate any known law of physics. The total energy of a universe can be balanced by its gravitational energy, meaning that the creation of a universe from a quantum fluctuation may cost nothing at all. If this picture is correct, then the birth of universes is not a rare or miraculous event, but an ongoing process, a natural consequence of the restless quantum vacuum that keeps the multiverse growing. A brief surge of energy at the tiniest scales might balloon into an entire cosmos. The idea that a universe could grow from a microscopic seed sounds fantastical, but it is precisely what the theory of cosmic inflation describes. During the inflationary epoch, a patch of space smaller than an atom expanded by a factor of at least 10 to the power of 26 in a tiny fraction of a second, growing into a region large enough to encompass everything we can observe today. The energy that drove this expansion came from the inflaton field, a quantum field that filled the early universe with a uniform, high-energy state. If a similar burst of inflation could be triggered by a quantum fluctuation in the vacuum, then a new universe could be born from almost nothing, inflating from a subatomic speck to a vast, expanding cosmos in the blink of an eye. The process would be invisible to us, taking place in a region of space that quickly becomes causally disconnected from our own. But within that new bubble, galaxies, stars, and perhaps even life could eventually emerge, all from a fleeting disturbance in the quantum vacuum. Some universes could have stars that burn cold and dark, invisible to human eyes. In our universe, stars shine brightly because the nuclear reactions in their cores produce enormous quantities of energy in the form of visible light. But the spectrum of light a star emits depends on the physical constants that govern nuclear physics and electromagnetism. In a universe where these constants take different values, the fusion reactions might proceed at a much lower temperature, producing photons with wavelengths far outside the visible range. Such stars would still be powered by nuclear fusion, but their light would be entirely invisible to eyes like ours. They might radiate predominantly in the infrared, the microwave, or even the radio portion of the spectrum, bathing their planets in a warmth that we could feel but never see. Life forms that evolved around such stars would perceive a very different kind of light, one that we have no natural sense to detect. The night sky in such a universe would appear completely dark to a human visitor, even though it might be teeming with activity and energy in wavelengths beyond our perception. They might release energy in wavelengths we have no names for. The electromagnetic spectrum in our universe extends from radio waves through microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. We have names and instruments for each of these ranges because they exist in our universe and play roles in our physics. But in a universe with fundamentally different constants, entirely new types of radiation might exist that have no analog in our experience. The structure of the electromagnetic spectrum depends on the properties of charged particles and the nature of the electromagnetic force. And if these differ, the radiation that results could be qualitatively different. It might propagate at a different speed, interact with matter in unfamiliar ways, or carry energy in patterns that our mathematics would struggle to describe. We have no vocabulary for such radiation because we have never encountered it, and our instruments, designed to detect the specific kinds of radiation that exist in our universe, would be useless. The diversity of possible radiation in the multiverse is a humbling reminder that our knowledge of physics is necessarily parochial, shaped by the particular constants of the universe we happen to inhabit. There may be universes where gravity is repulsive instead of attractive. In our universe, gravity is always attractive. Every object with mass pulls every other object towards it. This is what holds planets in orbit, keeps your feet on the ground, and binds galaxies into clusters. But there is no logical necessity for gravity to work this way in every possible universe. The cosmological constant in our universe already provides a form of repulsive gravity on the largest scales, driving the accelerating expansion of space. In a universe where the repulsive component of gravity dominates at all scales, every object would push every other object away. Matter would scatter outward rather than clumping together, and the familiar processes of gravitational collapse that form stars, planets, and galaxies would never occur. Such a universe would be a place of perpetual dispersal, where every particle races away from every other particle for all eternity. There would be no structure, no complexity, and no possibility of the gravitational embrace that allows our own cosmos to organize itself into the beautiful tapestry of light and matter we observe. In such a cosmos, matter would scatter forever, never forming stars or galaxies. If gravity were wholly repulsive, the consequences for cosmic structure would be devastating. In our universe, the story of structure formation is one of gravitational attraction. Tiny density fluctuations in the early universe grew over billions of years as gravity pulled matter together, eventually forming the galaxies, clusters, and filaments that we observe today. Without attractive gravity, this process simply could not happen. Instead of clumping together, matter would spread out more and more as time went on, filling space with an ever more uniform and ever more dilute distribution of particles. The temperature would drop relentlessly as each particle moved farther from its neighbors. There would be no regions of high density where nuclear reactions could ignite, no sources of energy to warm the drifting material, and no possibility of complexity emerging from the featureless uniformity. The universe would expand into a state of maximum dispersal, a cold, empty void in which nothing ever happens. It is a stark contrast to the rich, structured cosmos we inhabit, and it illustrates how sensitively the fate of a universe depends on the sign and strength of gravity. Time itself might not exist in certain universes. We take the flow of time for granted. It carries us from one moment to the next, gives meaning to cause and effect, and provides the stage on which the story of the universe unfolds. But time is not an inevitable feature of all possible realities. In some approaches to quantum gravity, time is not a fundamental ingredient of the universe, but an emergent property that arises from more basic structures. If the conditions that give rise to time were absent in another universe, that universe would exist as a timeless state, a single frozen configuration with no past and no future. There would be no sequence of events, no evolution, no aging, and no possibility of change. The concept of before and after would have no meaning. Such a universe is difficult to imagine from our time-bound perspective, because our very thoughts require time to unfold. But mathematically, timeless solutions to the equations of physics do exist, and in the vast landscape of the multiverse, such solutions may well be realized. A universe without time would be utterly alien, a silent, frozen tableau that simply is. Without time, everything would exist as a frozen state, with no before or after. A universe without time would not be dark or empty in the way we usually imagine. It would contain whatever configuration of matter and energy it was born with, but that configuration would never change. There would be no movement, no vibration, no radiation, and no decay. Light would not travel, because traveling requires time. Atoms would not interact, because interaction is a process that unfolds in time. The universe would be a single, static snapshot, a crystalline arrangement of matter fixed in place for all of eternity, except that the word eternity itself loses its meaning without time to measure it. There would be no observers and no experiences, because consciousness requires a succession of mental states, and succession requires time. From the outside, if such a perspective were possible, a timeless universe would look like a three-dimensional sculpture frozen in place, beautiful perhaps in its geometry, but devoid of the dynamism that makes our own cosmos so rich and so full of possibility. Some universes may contain no matter at all, only endless radiation streaming through space. In our universe, the balance between matter and radiation has shifted over cosmic history. In the earliest moments after the Big Bang, the universe was dominated by radiation, a hot, dense plasma of photons and other massless particles. As the universe cooled, matter gradually came to dominate, forming atoms, molecules, stars, and galaxies. But this transition depended on specific features of our physical constants, including the mass of the electron, the strength of the electromagnetic force, and the asymmetry between matter and antimatter. In a universe where these parameters differ, the transition to a matter-dominated era might never occur. Instead, radiation could remain dominant for all time, filling the universe with a featureless bath of photons that gradually cools as space expands. There would be no atoms, no molecules, no solid objects, and no surfaces. Just an endless, uniform glow of energy fading slowly into the void. Such a universe would be profoundly simple, a cosmos reduced to its most elementary state, a sea of light with nothing in it to cast a shadow. In an infinite multiverse, every possible history must eventually occur. If the multiverse is truly infinite, containing an unlimited number of universes, then the logic of combinatorics leads to an astonishing conclusion. Every history that is consistent with the laws of physics must be played out somewhere. Every possible sequence of events, every possible arrangement of particles, every possible outcome of every possible experiment exists in some universe within the collection. This is not a matter of probability, in the usual sense. It is a mathematical certainty arising from the fact that there are only a finite number of distinguishable states within any region of finite size, but an infinite number of such regions across the multiverse. The implication is profound. Somewhere, the entire history of our planet has unfolded in exactly the same way, but with one small difference. Somewhere, the asteroid that ended the age of the dinosaurs missed. Somewhere, the Library of Alexandria was never burned. Every story that could have been told has been told, is being told, and will be told in an infinite number of ways. There could be a universe where dinosaurs never went extinct. In our universe, the reign of the dinosaurs came to an abrupt end roughly 66 million years ago, when a massive asteroid struck what is now the Yucatan Peninsula, triggering a global catastrophe that wiped out roughly 3/4 of all species on Earth. This event was not inevitable. It was the result of a specific trajectory of a specific rock in a specific part of the solar system, a chain of events that could easily have unfolded differently. In the multiverse, there would be universes where the asteroid missed, or where it never existed in the first place. In those universes, the dinosaurs would have continued to evolve, diversify, and dominate the planet for tens of millions of additional years. The mammals that eventually gave rise to humanity in our timeline might have remained small, marginal creatures living in the shadows of their reptilian overlords. The course of life on that alternate Earth would have taken a path entirely different from our own, producing an ecosystem shaped by reptilian rather than mammalian evolution. Intelligent life, there might be reptilian, descended from raptors rather than primates. If the dinosaurs had survived and continued to evolve for another 66 million years, some lineages might have developed larger brains, more complex social behaviors, and the capacity for something resembling intelligence. Certain species of theropod dinosaurs, the group that includes the ancestors of modern birds, already showed signs of relatively high intelligence for their time, with large brains relative to body size and evidence of complex behavior. Given millions of additional years of evolution, it is not unreasonable to imagine that some descendant of these clever theropods could have developed the cognitive abilities that we associate with intelligence: tool use, language, abstract thought, and social organization. The result would be a civilization utterly unlike our own, built by beings with a reptilian body plan, a different sensory world, and a different evolutionary history. They would think differently, perceive the world differently, and build their societies according to principles shaped by their unique biology. It is a captivating thought experiment, a window into the extraordinary range of possibilities that the multiverse might contain. In another universe, humanity may have never evolved at all. The evolution of human beings was not an inevitable outcome of natural history. It depended on a long chain of contingent events, from the formation of the Earth at the right distance from the Sun to the specific pattern of mass extinctions that cleared the way for mammals, to the climate shifts that drove our ancestors onto the African savanna. Change any one of these events, and the trajectory of life on Earth could have taken a dramatically different course. In the multiverse, there would be countless versions of Earth where the conditions for human evolution simply never arose. Perhaps the asteroid that killed the dinosaurs struck at a different angle or at a different time, altering the course of mammalian evolution. Perhaps a different pattern of continental drift produced a different set of habitats, favoring entirely different lineages. On these alternate Earths, the forests would still grow and the oceans would still teem with life, but there would be no humans to contemplate the stars or wonder about the meaning of existence. Earth there could be filled with forests and oceans, but no human voices. Imagine a version of Earth where every river, mountain, and coral reef exists just as it does here, but where no human being has ever walked the surface. The forests would be vast and ancient, undisturbed by agriculture or industry. The oceans would be full of whales, sharks, and fish in numbers that our own depleted seas can barely remember. Birds would fill the skies, insects would hum in the meadows, and the night would be utterly dark, unmarked by the glow of cities. There would be no roads, no buildings, no language, and no art. The planet would still be beautiful, still teeming with life, still spinning through space in its quiet orbit around the sun. But there would be no one there to appreciate any of it, no consciousness to marvel at the sunset or to wonder what lies beyond the horizon. This imagined Earth is a reminder of how narrow and specific the conditions were that led to our existence, and of how easily the story of life could have unfolded without including us. Some universes could be filled entirely with black holes as far as reality stretches. In our universe, black holes form when the most massive stars collapse at the end of their lives, or when dense regions of matter are compressed beyond a critical threshold. They are relatively rare objects, scattered across the cosmos, in the cores of galaxies, and in the remnants of exploded stars. But in a universe with stronger gravity or more massive initial density fluctuations, the formation of black holes could be dramatically more common. If the conditions were right, nearly all the matter in such a universe could collapse into black holes, leaving a cosmic landscape dominated by these dark, gravitationally intense objects. The space between them would be almost entirely empty, and the only interactions would be the slow, silent mergers of black holes spiraling towards each other over unimaginable timescales. Such a universe would be one of the most extreme environments conceivable, a place where the geometry of space-time is warped into a labyrinth of event horizons and singularities, with no light and no hope of the kind of complexity that makes our own cosmos so interesting. Others may be so diffuse that galaxies never form and matter drifts forever. The formation of galaxies in our universe required a very specific set of initial conditions. Tiny fluctuations in the density of matter in the early universe, amplified by gravity over billions of years, grew into the vast cosmic web of filaments and clusters that we observe today. If those initial fluctuations were even slightly smaller, gravity would not have been strong enough to pull matter together on the scales needed to form galaxies. The universe would remain smooth and nearly uniform, a vast expanse of hydrogen and helium, gas slowly cooling and thinning as space expanded. There would be no dense regions where stars could ignite, no gravitational wells where planets could form, and no islands of matter where complexity could develop. The matter in such a universe would drift apart forever, each atom increasingly isolated from its neighbors, approaching but never quite reaching the emptiness of a perfect vacuum. It would be a universe of almost infinite space and almost zero content, a quiet, gentle cosmos that never quite achieves the concentration of energy needed to produce anything interesting. Some universes may only last a fraction of a second before collapsing. Not every universe in the multiverse need be long-lived. In fact, many possible configurations of physical constants would produce universes that are violently unstable, expanding for a brief moment before gravity overwhelms the expansion and pulls everything back together in a catastrophic collapse. Such a universe would flare into existence with a burst of energy, expand just long enough for its contents to begin to cool, and then reverse direction, contracting at an accelerating rate until all of its matter and energy is crushed back into a state of unimaginable density. The entire lifespan of such a universe might be measured in fractions of a second, far too short for any structure to form, let alone anything resembling life. These fleeting universes would be born and die in silence, leaving no record and no legacy. In the landscape of the multiverse, they may outnumber stable, long-lived universes like ours by an enormous margin, making our cosmos a rare and precious anomaly in a sea of brief, violent failures. They would flare into existence and vanish as though they never were. The image of a universe that lives and dies in a fraction of a second is both haunting and oddly beautiful. Such a universe would experience its entire history in less time than it takes a photon to cross an atom. There would be no era of star formation, no cooling of gases into galaxies, no gradual assembly of planets. The energy released in the initial expansion would barely have time to propagate before the collapse began, compressing everything back to the extraordinary density from which it came. From the outside, if any outside perspective were possible, the universe would appear as a brief flash, a momentary disturbance in the fabric of the multiverse that leaves no lasting trace. No information about its existence would survive, and no observer could ever have formed within it to witness its beginning or its end. These ephemeral universes are a reminder that stability is not guaranteed, that the conditions which allow a cosmos to persist long enough for anything interesting to happen are special and must not be taken for granted. There might be universes that recycle themselves endlessly in cosmic cycles. The cyclic model of the universe proposes that the cosmos does not have a single beginning and a single end, but instead undergoes an eternal sequence of expansions and contractions, each cycle producing a new Big Bang and a new period of cosmic evolution. In this picture, the universe expands, cools, and eventually contracts back to a state of extreme density, only to bounce and begin expanding again. Each cycle would produce its own generation of stars, galaxies, and possibly life, all of which would be erased in the subsequent contraction and replaced by entirely new structures in the next expansion. The cyclic model draws on ideas from brain cosmology, where the cycles are driven by the periodic collision and separation of parallel brains in a higher dimensional space. It is an ancient idea given modern mathematical form, echoing the cosmologies of several classical traditions that envisioned a universe of eternal return. Whether any universe in the multiverse actually follows such a cyclic pattern remains an open question, but the mathematics is consistent and the idea is deeply compelling. Such a cosmos would breathe, expanding and collapsing, birth and death repeating forever. The metaphor of a breathing universe captures something essential about the cyclic model. Just as a living creature inhales and exhales in a steady rhythm, the cyclic universe expands and contracts in a grand cosmic oscillation. Each expansion is a breath outward, filling space with energy, matter, and eventually the structures we associate with a living cosmos. Each contraction is a breath inward, drawing everything back together and erasing the details of the previous cycle. The transition between contraction and expansion, the bounce, is the moment of renewal, corresponding to a new Big Bang that resets the cosmic clock. In this vision, time does not begin and does not end. The universe has always been oscillating and always will be, each cycle lasting trillions of years, but forming only one breath in an eternal rhythm. There is something deeply calming about this image, the idea that the cosmos is not racing towards a final end, but gently pulsing through an infinite sequence of creation and dissolution, each cycle a fresh beginning within an eternal pattern. Some universes may be governed entirely by quantum randomness, with no stable laws. In our universe, the laws of physics appear to be stable and reliable. The same equations that describe the behavior of atoms today also described their behavior billions of years ago, and we expect them to continue doing so indefinitely into the future. But this stability is not guaranteed in every possible universe. In some regions of the multiverse, the vacuum state might not settle into a stable configuration, leaving the physical constants and even the laws themselves subject to constant fluctuation. In such a universe, the strength of gravity could change from moment to moment. The speed of light could vary from place to place, and the rules governing particle interactions could shift unpredictably. There would be no regularity, no repeatability, and no possibility of the kind of ordered development that produces stars, planets, and life. Science itself would be impossible in such a universe, because the very idea of a scientific law depends on the assumption that the rules do not change. A cosmos governed by pure quantum randomness would be a place of perpetual chaos. Others might follow strict deterministic laws, where everything is decided from the start. At the opposite extreme from quantum randomness lies the possibility of a universe governed by perfect determinism, where every event from the first moment of the Big Bang to the last flicker of the final star is fixed and inevitable. In our universe, quantum mechanics introduces a fundamental element of randomness, making the outcome of individual events inherently unpredictable. But in a universe with different foundations, quantum randomness might be absent or suppressed, leaving a cosmos that evolves like a perfectly wound clock. Every particle would follow a trajectory determined by the initial conditions, and the entire history of the universe would be encoded in the state of its first instant. There would be no genuine surprises, no outcomes that could have gone differently, and no room for the kind of indeterminacy that many philosophers associate with free will. Such a universe would be mathematically elegant, but existentially claustrophobic, a reality in which everything that will ever happen has already been decided by the conditions at the moment of creation. In a deterministic universe, free will would be an illusion written long ago. If the universe operates under perfectly deterministic laws, with no room for quantum randomness or genuine indeterminacy, then the actions of every being within it are fixed from the moment the universe begins. Your thoughts, your decisions, and your feelings would all be the inevitable results of the initial arrangement of particles at the start of time, unfolding with the same mechanical precision as the orbit of a planet. The sensation of choosing freely would still exist, because the brain would still process information and weigh options in the same way, but the outcome of every deliberation would already be determined. Free will, in this picture, is not something you exercise, but something you experience, a subjective feeling generated by a process whose result was decided long before you were born. This is one of the oldest questions in philosophy, given new depth by the multiverse. In some universes, determinism reigns and free will is an illusion. In others, quantum randomness preserves a genuine element of unpredictability. The multiverse allows both possibilities to coexist. Some physicists believe the multiverse could be infinite in every direction. The question of whether the multiverse is finite or infinite is one of the most profound in all of cosmology. Some models of eternal inflation suggest that the inflating region of space is spatially infinite, extending without limit in every direction. Within this infinite expanse, an infinite number of bubble universes are constantly forming, each one expanding into its own pocket of space. If the multiverse is infinite, then there is no boundary, no edge, and no center. Every point is surrounded by an endless sea of other universes, stretching out in all directions forever. This possibility challenges our intuition about the nature of existence in the deepest possible way. We are accustomed to finite things, things that have beginnings and endings, edges and boundaries. An infinite multiverse has none of these features. It simply goes on, without limit or termination. The sheer scope of an infinite multiverse is humbling beyond measure, making even the largest objects in our own universe, galaxy clusters and cosmic voids, seem vanishingly small by comparison. If the multiverse is truly infinite, then this very moment exists elsewhere endlessly. In an infinite multiverse, every configuration of matter and energy that is physically possible must be realized, not just once, but an infinite number of times. This means that the specific arrangement of atoms that constitutes your body, your room, and the air around you at this very moment is duplicated an infinite number of times across the multiverse. Somewhere in an unimaginably distant region of reality, another version of you is lying in the same position, thinking the same thoughts, breathing the same breath. And beyond that duplicate, there is another and another, extending without end. The idea is not a poetic exaggeration, but a mathematical consequence of infinity. As long as the probability of any given configuration is greater than zero, an infinite multiverse guarantees that it occurs infinitely often. The thought is simultaneously comforting and bewildering, suggesting that this moment, for all its apparent ordinariness, is not a one-off event, but a recurring pattern woven endlessly into the fabric of an infinite reality. A universe with slightly different physical constants might collapse instantly. The stability of our universe depends on a delicate balance between the forces that drive expansion and the forces that pull matter together. The cosmological constant, the energy density of empty space, plays a crucial role in this balance. In our universe, it is extremely small and positive, producing a gentle acceleration of the expansion. But if the cosmological constant were large and negative, the effect would be reversed. The universe would collapse under its own gravitational pull almost as soon as it formed. The collapse would be swift and total, compressing all the matter and energy in the universe back to a state of extraordinary density within a tiny fraction of a second. There would be no time for stars to form, no time for planets to cool, and no time for complexity of any kind to develop. The universe would live and die in an instant, a brief flicker of existence snuffed out by the overwhelming inward pull of its own vacuum energy. In the string landscape, such unstable vacua may vastly outnumber the stable ones, making our universe a fortunate exception. Another, with different constants, might never stop expanding into eternal emptiness. At the other extreme, a universe with a cosmological constant that is too large and positive would expand so rapidly that matter could never concentrate into structures. In our universe, the expansion is slow enough that gravity can pull matter together into galaxies, stars, and planets. But if the outward push of the vacuum energy was significantly stronger, it would overcome gravity at every scale, tearing apart clouds of gas before they could collapse and preventing even the formation of atoms into molecules. The universe would expand and thin out without limit, the density of matter dropping exponentially until each particle was effectively alone in an infinite void. There would be no galaxies, no stars, no planets, and no light. Just an endless, cold, empty expanse growing ever more diffuse with each passing moment. Eventually, even the cosmic microwave background radiation would be stretched to such long wavelengths that it would be undetectable. The universe would approach a state of perfect emptiness, a cosmic vacuum that endures forever, expanding into nothing. Some universes could allow elements beyond our periodic table to exist. The periodic table of elements in our universe contains roughly 90 naturally occurring elements, from hydrogen to uranium, with a handful of heavier elements produced briefly in laboratories and in extreme astrophysical events. The number and properties of these elements are determined by the fundamental forces that govern nuclear physics, particularly the balance between the strong nuclear force and the electromagnetic repulsion of protons. In a universe where these forces take different values, the landscape of possible elements could be dramatically altered. A stronger nuclear force might allow nuclei with far more protons to hold together stably, producing super-heavy elements that do not exist in our universe. These elements could have chemical properties entirely unlike anything on our periodic table, capable of forming compounds and structures that we cannot even begin to imagine. A universe rich in exotic elements would host a chemistry far more complex and varied than our own, opening up possibilities for materials, minerals, and perhaps even biology that have no counterpart in the cosmos we inhabit. Others may not allow chemistry to exist at all, leaving only a formless soup of particles. Chemistry, as we know, it depends on the existence of stable atoms, and stable atoms depend on a precise balance between the electromagnetic force and the strong nuclear force. The electromagnetic force holds electrons in orbit around the nucleus, while the strong force binds protons and neutrons together inside the nucleus. If either of these forces were significantly different, atoms as we know them would not form. Without stable atoms, there would be no molecules, no chemical reactions, and no possibility of the complex structures that underpin life. The universe would be filled with a formless soup of subatomic particles, quarks, electrons, and photons milling about without ever combining into anything more structured. It would be a cosmos of ultimate simplicity, where nothing is built, nothing grows, and nothing changes. The contrast with our own chemically rich universe could not be starker. Our cosmos is a place of extraordinary structural complexity, from the delicate architecture of a snowflake to the intricate machinery of a living cell, and all of it depends on the specific values of the constants that allow chemistry to happen. Somewhere stars might shine with colors our eyes cannot imagine. The colors that a star emits depend on its surface temperature, which in turn depends on the nuclear reactions in its core and the physical constants that govern them. In our universe, stars range in color from deep red to brilliant blue, a spectrum that our eyes have evolved to perceive. But in a universe with different physical constants, the range of stellar temperatures could be entirely different. Stars might burn at temperatures that produce radiation exclusively in the ultraviolet or infrared, wavelengths that are invisible to our eyes. Or they might produce light at wavelengths that do not exist on our electromagnetic spectrum at all, if the nature of photons and their interactions with matter are fundamentally altered. To beings that evolved in such a universe, these colors would be as natural and familiar as red and blue are to us. They would have senses tuned to detect the radiation their stars produce, and their experience of beauty and color would be shaped by a palette we can never access. The thought expands the imagination, hinting at aesthetic experiences that lie forever beyond human perception. Some universes could be only two-dimensional, where everything is flat. The idea of a two-dimensional universe might seem whimsical, but it has been studied seriously by physicists and mathematicians. In a universe with only two spatial dimensions, all objects would be flat, and all movement would be confined to a plane. The physics of such a universe would differ profoundly from our own. Gravity, for instance, would not follow an inverse square law, but an inverse first power law, changing the way orbits and structures behave. The possibilities for complexity in such a world are surprisingly rich. Theoretical studies have shown that two-dimensional universes can support analogs of atoms, molecules, and even living creatures, though the details of their chemistry and biology would be quite different from anything we know. The concept was famously explored in Edwin Abbott's novel Flatland, which imagined a society of two-dimensional beings unaware of the existence of a third dimension. In the multiverse, universes with fewer spatial dimensions than ours may be far more common than we expect, each one a self-contained reality with its own version of physics and its own possibilities for order and complexity. Others might unfold across 10 or 11 dimensions, far richer than ours. While some universes in the multiverse might have fewer spatial dimensions than ours, others could have many more. String theory and M-theory naturally operate in 10 or 11 dimensions, and in some compactification schemes, several of these dimensions could be large and accessible. A universe with 10 spatial dimensions would be incomprehensibly richer than our own. Objects would have far more degrees of freedom. The geometry of space would allow for structures that have no three-dimensional analog, and the forces of nature would behave in ways that defy our intuition. A being native to such a universe would find our three-dimensional world painfully confining, much as we would find life on a flat, two-dimensional surface impossibly restricting. The extra dimensions would allow for new types of particles, new types of forces, and new types of matter, creating a physics that is qualitatively different from anything we experience. In the landscape of the multiverse, the number of spatial dimensions is just one more parameter that can vary, adding yet another axis along which the diversity of possible realities unfolds. In some universes, dark matter might not exist, leaving galaxies unable to form. Dark matter is the invisible scaffolding that holds galaxies together in our universe, its gravitational pull keeping stars from flying apart as they orbit. In some regions of the multiverse, this mysterious substance might simply not exist at all. Without dark matter, galaxies would struggle to form because there would be no invisible framework to gather ordinary matter into dense enough clumps. Stars might still ignite here and there, but they would drift alone through vast emptiness, never clustering into the spiraling structures we know so well. The cosmic web of filaments and voids that shapes our observable universe would be absent, replaced by a featureless expanse of thinly scattered gas. Planets would be exceedingly rare, and the conditions for complex chemistry would be almost impossible to achieve. Such a universe might glow faintly with the light of isolated stars, each one surrounded by nothing but silence and cold. It would be a cosmos stripped of its hidden architecture, beautiful perhaps in its emptiness, but profoundly lonely. In others, dark matter could dominate everything, drowning ordinary matter in invisible mass. In our universe, dark matter outweighs ordinary matter by roughly 5-to-1, shaping the large-scale structure of the cosmos from behind a veil of invisibility. In some other universe, that ratio could be far more extreme, with dark matter dominating everything and leaving ordinary matter as a mere trace. Such a cosmos would be governed almost entirely by invisible forces, with vast halos of dark matter pulling and stretching space in ways that visible matter could barely influence. Stars and planets might still form, but they would be scattered thinly across an overwhelming ocean of unseen mass. Galaxies could grow immensely large, their gravitational wells deepened by dark matter to an extraordinary degree. Light from those few stars would travel through a universe whose structure was dictated by something no eye could ever detect. The visible portion of reality would be a tiny afterthought, a faint shimmer on the surface of a dark and silent ocean. For any life that somehow emerged, the true nature of their cosmos would be almost entirely hidden from view. Some universes may have far more powerful black holes than ours. Black holes in our universe are already among the most extreme objects known, bending space and time to their limits and swallowing everything that crosses their event horizons. In some other universe, the fundamental constants might conspire to make black holes far more powerful than anything we have observed. Gravity could be stronger, allowing collapsing stars to form singularities with even greater mass and reach. The event horizons of such black holes might stretch across distances that dwarf entire star systems, pulling in matter from unimaginable volumes of space. Accretion disks around them could blaze with energies that would tear apart the fabric of nearby space-time. These colossal gravitational engines might dominate the structure of their universe, shaping galaxies and consuming stars at a pace we would find terrifying. Entire regions of space could be hollowed out, leaving only the quiet hum of radiation leaking from the edges of these vast dark spheres. In such a universe, darkness would not merely lurk between the stars, but actively consume the light itself. In others, stars might never ignite at all, leaving only frozen clouds of gas. Stars ignite when clouds of hydrogen gas collapse under their own gravity until the core becomes hot and dense enough for nuclear fusion to begin. In some universes, the conditions for this process might never be met. If the gravitational constant was slightly weaker, or if the strong nuclear force were a fraction less powerful, gas clouds might collapse, but never reach the critical threshold for fusion. Instead, they would settle into vast, cold spheres of compressed gas, glowing faintly with residual heat, but never truly shining. The universe would be filled with these silent, frozen clouds drifting through endless darkness. Without stars, there would be no heavy elements forged in stellar cores, no planets built from stardust, and no warmth to sustain any form of chemistry. Such a cosmos would remain perpetually cold and dark, a vast nursery of stillborn suns. It would be a universe where the raw materials for creation exist in abundance, yet the spark that brings them to life never arrives. Somewhere life may flourish in unimaginable forms we would never recognize. Life on Earth is built from carbon, sustained by liquid water, and powered by the energy of our sun, but these are only the ingredients that happen to work in our particular universe. Somewhere in the multiverse, life might arise from entirely different foundations, using elements and processes we have never imagined. Organisms could be built from silicon or boron, drawing energy from radiation or chemical reactions that do not exist in our cosmos. They might perceive reality through senses we have no words for, detecting forces or fields that our physics does not describe. Their bodies could be vast and diffuse, spread across clouds of gas, or impossibly small, thriving at scales far below the atomic. The very definition of what it means to be alive might need to be rewritten in such a universe. Intelligence could emerge in forms that bear no resemblance to brains or nervous systems, thinking in patterns we would never recognize as thought. If we ever glimpsed such life, we might not even understand that we were looking at something alive. Creatures might emerge in oceans of liquid helium or within vast clouds of plasma. On Earth, the chemistry of life depends on liquid water, a substance that exists within a narrow range of temperatures and pressures perfectly suited to our planet. In another universe, the conditions for life might center on entirely different substances, such as liquid helium or vast clouds of plasma. Liquid helium exists at temperatures close to absolute zero, where quantum effects dominate and matter behaves in deeply unfamiliar ways. Creatures born in such an environment might move through superfluid oceans with no friction at all, gliding in silence through a world of extreme cold. Alternatively, life could emerge within plasma, the superheated state of matter found in stars, where charged particles dance in magnetic fields. Such beings might have no solid form at all, existing as organized patterns of energy and charge. Their thoughts, if they had them, might travel at the speed of electrical impulses through ionized gas. These possibilities remind us that life, as a concept, may be far more flexible and resilient than our earthly experience suggests. Other universes might be eternally sterile and lifeless despite having stars and planets. Having stars and planets does not guarantee that life will follow. In some universes, the right conditions for chemistry might simply never align, even if galaxies, solar systems, and rocky worlds exist in abundance. The chemical pathways that led from simple molecules to self-replicating structures might be blocked by subtle differences in the laws of physics. Perhaps the bonds between atoms are too weak to form complex molecules, or the energy available from starlight falls in wavelengths that cannot drive useful reactions. Planets in such a universe might have oceans and atmospheres, but their surfaces would remain barren for eternity. No cell would ever divide, no organism would ever stir, and no mind would ever wonder at the stars above. The silence of such a cosmos would be absolute, a vast stage set for a performance that never begins. It is a sobering thought that the mere existence of worlds is not enough, that life requires a very particular set of circumstances that some universes may never provide. A universe could exist where light travels at a different speed. The speed of light in our universe is roughly 300,000 kilometers per second, a constant that shapes everything from the structure of atoms to the expansion of space itself. In another universe, light might travel at a completely different speed, and the consequences would ripple through every aspect of reality. If light was slower, the universe would feel smaller and more intimate, with information and energy taking longer to cross even modest distances. If it were faster, space would seem to stretch more freely, and events across vast distances could influence one another more quickly. The relationship between energy and mass, captured in the famous equation relating them, would shift dramatically, altering the behavior of every particle and every force. Stars might burn differently, atoms might hold together in unfamiliar ways, and the passage of time itself could feel altered. A universe with a different speed of light would not merely look different, but would operate according to a fundamentally different rhythm. Even the colors of a sunset, if sunsets existed there, would be unrecognizable to our eyes. If light traveled faster, space might stretch more quickly, and galaxies would grow thinner. If light traveled faster than it does in our universe, the effects would cascade through every corner of reality in unexpected ways. Space itself might expand more rapidly because the speed of light is intimately linked to the rate at which the cosmos stretches. Galaxies would grow thinner and more diffuse, their stars spread across greater volumes as the fabric of space-time relaxed under less restrictive speed limits. The energy carried by each photon would shift, potentially making starlight hotter or cooler depending on the precise change. Communication across cosmic distances would become easier in principle, but the vast expansion of space might cancel out any advantage. Atoms themselves would behave differently because the electromagnetic force that holds electrons in orbit depends on the speed at which light carries that force. Chemistry would change, and with it, the possibility of complex molecules and life. In such a universe, the familiar dance of matter and light would be rewritten, producing a cosmos that might be recognizable in outline but deeply alien in its details. In another universe, nothing might travel faster than walking pace. Imagine a universe where the ultimate speed limit, the cosmic speed of light, was no faster than a gentle walking pace. In such a cosmos, everything would unfold with an almost unbearable slowness. Light from a nearby object would take noticeable time to reach your eyes, and the world around you would appear as a delayed, ghostly projection of the recent past. Energy and information could never rush ahead, meaning that cause and effect would crawl forward at a pace that feels almost frozen. Stars might still exist, but their light would take unimaginable eons to travel even short distances, leaving the sky permanently dark to any observer. Gravity would propagate slowly too, meaning that orbits and cosmic structures would behave in ways our physics can barely model. The very concept of urgency would have no meaning in such a universe, because nothing could ever happen quickly. It would be a cosmos of infinite patience, where every event unfolds like a dream in slow motion, gentle and unhurried beyond all measure. There may be universes where entropy runs in reverse and order builds naturally. In our universe, entropy always increases, meaning that order gradually breaks down into disorder over time. Heat spreads, structures decay, and the cosmos slowly drifts towards a state of maximum randomness. But in some other universe, this fundamental arrow might point in the opposite direction. Entropy there could run in reverse, with disorder naturally giving way to greater and greater order. Scattered particles might spontaneously assemble into complex structures without any external input. Broken things would mend themselves, diffuse gases would gather into stars, and chaos would quietly organize itself into intricate patterns. Such a universe would feel deeply strange to us, as though time were flowing backwards even while events moved forward. The second law of thermodynamics, which governs so much of our reality, would simply not apply. In its place, a universe of perpetual self-organization would hum quietly, building ever more elaborate structures from the simplest beginnings. Some universes might not have space as we understand it, only a network of nodes. We experience space as a smooth, continuous fabric stretching in every direction, a backdrop against which matter moves and events unfold. But some theoretical frameworks suggest that space might not be continuous at all. In certain universes, what we think of as space could be replaced by a network of discrete nodes, tiny points connected by relationships rather than distances. There would be no smooth expanse between objects, only connections linking one node to the next in an intricate web. Movement would mean hopping from node to node rather than gliding through empty space. The very concept of distance would need to be redefined, measured not in meters or light years, but in the number of connections between points. Such a universe would have no horizon, no smooth curvature, and no familiar sense of direction. Reality there would resemble an immense graph rather than a landscape, a structure of pure relationship with no background at all. It is a vision of existence stripped down to its most abstract and mathematical bones. Others may not have time, existing as an eternal frozen state. Time in our universe is the dimension that allows change to happen, the silent current that carries events from past to future. Without it, nothing could move, grow, decay, or evolve. Some universes in the multiverse might lack time entirely, existing as a single eternal frozen state with no progression whatsoever. Every particle, every field, every relationship would be fixed in place forever, like a photograph that never changes. There would be no sequence of events, no cause followed by effect, and no possibility of anything ever being different from what it is. Such a universe would contain structure, perhaps even complexity, but it would be a static complexity, forever locked in one configuration. No observer could ever exist there, because observation itself requires the passage of time to process information. It would be a universe of pure geometry, silent and still, existing without beginning or end. In a sense, it would be the most peaceful cosmos imaginable, a place where nothing ever stirs and nothing ever will. Some universes may allow instant communication across any distance. In our universe, the speed of light sets an absolute limit on how quickly information can travel from one place to another. This means that distant parts of the cosmos are effectively isolated from each other, unable to exchange messages faster than light allows. In some other universe, however, this restriction might not exist. Instant communication across any distance could be woven into the very fabric of space-time, allowing signals to leap from one end of reality to the other without delay. The implications would be profound, because any event anywhere would be immediately known everywhere. Cause and effect would become tangled in ways our physics cannot describe, with consequences arriving before their causes in some frames of reference. The structure of such a universe would be deeply interconnected, every point linked to every other in a web of instantaneous influence. Civilizations, if they arose, could share knowledge across galactic distances without ever waiting. It would be a cosmos without loneliness, where no corner of reality is ever truly far away. Others may be locked in total isolation forever, each particle unable to interact. Interaction is the foundation of everything we know. Gravity pulls matter together, electromagnetism binds atoms, and the nuclear forces hold particles in place. Without these interactions, nothing meaningful could ever happen. In some universe, every particle might be locked in total isolation, utterly unable to influence or even detect any other particle around it. Each point of matter would drift alone through an empty void, surrounded by countless others, but connected to none. No forces would reach across the gaps between them, no signals would pass, and no structures would ever form. Stars, planets, molecules, and life would all be impossible in such a cosmos. It would be a universe of infinite solitude, where every particle exists in its own private reality, unaware that anything else is there. The silence would not merely be an absence of sound, but an absence of connection itself. Such a universe would be the loneliest place imaginable, a vast collection of isolated points with no story ever told between them. In certain universes, stars may form from exotic particles unknown to us. The stars in our universe are built from hydrogen and helium, the simplest and most abundant elements in the cosmos. Their cores burn through nuclear fusion, converting lighter elements into heavier ones and releasing the energy that lights up the night sky. In some other universe, the particle zoo might be entirely different, filled with exotic particles that have no counterpart in our physics. Stars there might form from these unfamiliar building blocks, igniting through fusion processes we have never conceived. The light they produce could carry energies and wavelengths that fall outside anything our instruments could measure. Their lifespans could be wildly different, burning for mere moments or enduring for eons beyond our comprehension. The heavy elements forged in their cores would be substances unknown to our periodic table, capable of forming structures and chemistry we cannot predict. Planets orbiting such stars might be built from materials that behave in ways we would find utterly alien. It is a humbling reminder that the stars we know are only one possible answer to the question of how matter can shine. Some universes could be composed entirely of antimatter rather than matter. In our universe, matter overwhelmingly dominates over antimatter, a fact that puzzles physicists because the Big Bang should have produced equal amounts of both. Somewhere in the multiverse, that asymmetry might have tipped the other way, creating a universe composed entirely of antimatter. Antiprotons, positrons, and antineutrons would take the place of their ordinary counterparts, forming anti-atoms, anti-molecules, and eventually anti-stars and anti-planets. To an observer living inside such a cosmos, everything would seem perfectly normal because the laws of physics treat matter and antimatter almost identically. Stars would shine, chemistry would proceed, and life might even evolve, all built from the mirror image of what we are made of. The difference would only become apparent if matter from our universe ever came into contact with theirs, because matter and antimatter annihilate on contact in a burst of pure energy. Such a collision between universes would be unimaginably violent. For now, the antimatter universe would simply carry on in quiet parallel, a perfect reflection we would never know existed. Others might be flooded with energy, but contain no structure at all. Structure in our universe arises because matter can clump together under gravity, forming stars, galaxies, and planets. But what if a universe were flooded with so much energy that no structure could ever take hold? In such a cosmos, space would be saturated with radiation, particles, and fields all vibrating at immense intensities. The energy would be so overwhelming that any attempt by matter to gather into clumps would be instantly disrupted. Gravity would be overpowered, molecular bonds would be impossible, and even atoms might struggle to hold together. The universe would be a seething ocean of pure energy with no islands of calm where complexity could emerge. There would be no stars to light the void, no planets to orbit them, and no quiet corners where chemistry could unfold. It would be a cosmos of raw power but no form, a boundless storm with no harbor. Such a universe might be the most energetic place in the multiverse, yet also the most empty in every way that matters to life. The multiverse may be infinite not just in space, but also in time. We often think of the multiverse as infinite in space, stretching endlessly in every direction, but it may also be infinite in time. Some theoretical models suggest that the multiverse has no beginning and no end, that universes have been forming and dissolving for all of eternity. There was never a first moment, never a spark that started it all, only an endless procession of cosmic births and deaths, stretching backwards and forwards without limit. Our own Big Bang in this picture would be just one event among infinitely many, a single note in a symphony that has been playing forever. The concept of infinity in time is even harder to grasp than infinity in space, because it challenges our deepest intuitions about origins and endings. We naturally ask where it all started, but in a temporally infinite multiverse, that question has no answer. The multiverse simply is, and always has been, and always will be. It is a thought that can feel overwhelming or deeply calming, depending on how you hold it in your mind as you drift towards sleep. Some universes may be older than eternity itself, existing without ever beginning. The idea that some universes may be older than eternity itself is a concept that stretches language to its breaking point. In our universe, time began roughly 14 billion years ago with the Big Bang, giving us a clear starting point. But some cosmological models suggest that other universes might have existed for spans of time that have no meaningful comparison, stretching back through durations that make our billions of years feel like the blink of an eye. These universes might have persisted through countless cycles of expansion and contraction, or they might have existed in a timeless state before eventually developing a flow of time. The word eternity usually means forever, but when applied to these ancient universes, even that word feels insufficient. Such a cosmos would carry within it a depth of history so vast that no mind could comprehend it. Every possible event might have already occurred there, every possible configuration of matter explored and exhausted. It is a vision of existence that inspires both wonder and a gentle sense of insignificance, a reminder that time itself may have depths we cannot fathom. Some universes could contain physical laws that evolve and shift over time. In our universe, the laws of physics appear to be constant, the same today as they were billions of years ago, and presumably the same everywhere in the cosmos. But this constancy might not be universal. In some regions of the multiverse, the laws of physics themselves could evolve and shift over time, changing gradually like the seasons of an impossibly long year. Gravity might grow stronger or weaker as eons pass. The speed of light could drift, and the forces that hold atoms together might loosen or tighten. A universe with shifting laws would be a place of constant transformation, where the rules that govern matter today would not be the same rules that governed it a billion years earlier. Stars that once burned brightly might find their nuclear fires dimming as the strong force weakens, while new forms of matter might emerge as different constants rise. Life in such a universe would need to adapt not just to changing environments, but to changing physics itself. It is a vision of reality as something fluid and alive, a cosmos where even the foundations are never truly settled. Others might be frozen, unchanging, and static for all of existence. While some universes might have laws that evolve, Others could be the complete opposite, locked in a state of absolute rigidity for all of existence. In such a cosmos, nothing would ever change, not a single particle would shift its position, not a single photon would travel from one place to another. The universe would exist as a single unchanging configuration, a frozen sculpture of matter and energy suspended in perfect stillness. There would be no motion, no heat, no flow of time in any meaningful sense. Every relationship between every particle would be fixed from the very first instant, if such a universe even had a first instant. It would be a cosmos of pure being without any becoming, a place where existence is reduced to its simplest possible state. No observer could ever arise within it, because observation requires change, and change is precisely what this universe does not allow. It would be a monument to stillness, a reminder that existence does not require motion or narrative or purpose. Such a universe would simply be silent and complete for all of eternity. Some universes may expand into nothingness and then vanish completely. Some universes in the multiverse might be destined for the most complete ending imaginable. They could expand at an accelerating rate, stretching space faster and faster until every structure within them is torn apart. First, galaxies would separate beyond the reach of light, then stars would drift apart within those galaxies, then planets would be pulled from their orbits, and eventually atoms themselves would be ripped to pieces. But the expansion might not stop there. Space itself could stretch so thin that it reaches a kind of nothingness, a state where even the vacuum loses its properties and reality dissolves. The universe would not collapse or fade, but simply cease to exist, pulled apart into a void so absolute that even the concept of space no longer applies. It would be a cosmos that writes its own ending by expanding beyond the limits of existence itself. Such a universe would leave no trace, no echo, and no memory. It would vanish as completely as if it had never been, swallowed by the very emptiness it helped to create. Others might collapse into singularities and be reborn again in cycles. Some cosmological models propose that certain universes do not simply end, but collapse back upon themselves and are reborn in an endless cycle of creation and destruction. After expanding for billions of years, such a universe would reach a turning point where gravity overwhelms the expansion and everything begins to fall inward. Galaxies would rush towards each other, stars would merge, and all of space would compress into an unimaginably dense point, a singularity where the laws of physics as we know them break down. But rather than true destruction, this collapse might trigger a new Big Bang, an explosion of energy and matter that births an entirely new universe from the ashes of the old. Each cycle could produce a cosmos with slightly different constants and laws, an endless experiment in possibility. The universe would breathe, expanding and contracting like a cosmic heartbeat, each pulse bringing forth a new reality. No memory would survive from one cycle to the next, and every rebirth would be a fresh beginning. It is a vision of existence as rhythmic and eternal, a quiet drumbeat echoing through infinity. Somewhere black holes may act as portals between universes. Black holes in our universe are places where gravity becomes so intense that nothing, not even light, can escape. But some theoretical physicists have wondered whether the interior of a black hole might connect to another universe entirely. If the singularity at a black hole's center does not simply crush matter into nothingness, but instead opens a passage to a different region of space-time, then black holes could serve as portals between universes. Falling into one would mean leaving our cosmos behind and emerging somewhere else entirely, in a universe with its own stars, its own laws, and its own history. The journey would not be gentle, as the tidal forces near a black hole would stretch and compress any traveler beyond recognition. But in principle, the connection might exist, a doorway hidden behind an event horizon. Our own universe might have been born through such a passage, spilling out from a black hole in some parent cosmos. If this is true, then the black holes scattered across our skies are not just gravitational tombs, but potential gateways to realities we have never imagined. Some universes could be filled with wormholes, like cosmic highways connecting distant points. While black holes might serve as one-way portals, wormholes offer a more tantalizing possibility, a two-way connection between distant points in space or even between different universes. In some regions of the multiverse, wormholes could be stable and abundant, threading through the fabric of space-time like tunnels through a mountain. A universe filled with such structures would be a cosmos of shortcuts, where vast distances could be crossed in an instant by stepping through one of these cosmic highways. Travel between galaxies or even between universes might be as simple as finding the right entrance. The geometry of such a cosmos would be extraordinary, a tangled web of connections linking places that would otherwise be impossibly far apart. Civilizations in such a universe might spread across countless star systems without ever needing to travel at the speed of light. The very concept of distance would lose much of its meaning when any two points could be connected by a hidden passage. It would be a universe built for exploration, a labyrinth of doorways waiting quietly to be discovered. Others may be sealed off completely, with no way to connect across distances. Not all universes in the multiverse would be so well connected. Some might be sealed off entirely, with no portals, no wormholes, and no way for anything inside them to reach the outside. Every particle within such a universe would be trapped there forever, unable to cross the boundary into any other cosmos. The edges of reality, if they had edges, would be impenetrable walls beyond which nothing exists. No signal could leave, no traveler could escape, and no information about the outside multiverse could ever filter in. For any beings that arose within such a universe, the multiverse would be not merely invisible, but genuinely unreachable, a theoretical idea with no possible confirmation. Their cosmos would be a closed box, complete and self-contained, with no hint that anything lies beyond. The isolation would be total, not just physical, but conceptual, because even the idea of an outside would be untestable. Such a universe would be a perfect island in the multiverse, drifting alone through the vastness of possibility with no bridge to anywhere else. Some universes might allow civilizations billions of years older than ours. Our universe is roughly 14 billion years old, and the first complex civilizations on Earth emerged only a few thousand years ago. In the grand timeline of our cosmos, intelligent life is an extraordinarily recent development, but in some other universe, conditions might have allowed civilizations to arise billions of years earlier than they did here. If the first stars formed sooner, if rocky planets cooled more quickly, and if the chemistry of life proceeded faster, then intelligent beings might have been building societies when our universe was still young and featureless. By now, such civilizations could be incomprehensibly advanced, having harnessed energies and technologies that lie far beyond anything we can imagine. They might have mapped their entire cosmos, understood every law of physics, and perhaps even found ways to reach across the boundaries of their universe. The depth of knowledge accumulated over billions of years of continuous development would make our entire history of science look like the first tentative scribbles of a child. It is both an awe-inspiring and humbling thought to consider what intelligence could achieve given enough time. Others may end before life ever has a chance to begin. Not every universe in the multiverse would be given enough time for life to emerge. Some might end before the conditions for biology ever have a chance to develop. If the expansion rate were too fast, the universe could tear itself apart before stars had time to form. If it were too slow, gravity could pull everything back into a singularity before the first generation of stars had finished burning. Even if stars did form, the heavy elements needed for rocky planets and complex chemistry might not be produced in sufficient quantities before the universe met its end. Life requires a very specific window of cosmic time, long enough for stars to forge heavy elements, for those elements to gather into planets, and for chemistry to produce self-replicating molecules. Some universes might simply close that window before it has fully opened. Such a cosmos would be a brief candle, burning brightly for a moment and then going dark, never knowing what it might have become. It would be a universe of pure potential, forever unfulfilled, a whispered possibility that fades before it can be heard. Some universes might be unimaginably strange, with no analogies in our world. Among all the universes in the multiverse, some might be so alien that no analogy from our world could capture their nature. We describe other universes by comparing them to what we know, talking about different forces, different particles, different dimensions. But some universes might be built on principles so unlike our own that even these comparisons break down. There might be no space, no time, no matter, and no energy in any form we would recognize. The very categories we use to understand reality might not apply there at all. Instead, such universes could be governed by structures and relationships that no human language or mathematics has ever described. We cannot picture them because our imagination is shaped by our own universe, and these hypothetical realities lie entirely outside that frame. They would be as incomprehensible to us as color is to someone who has never seen, or music to someone who has never heard. The multiverse, in its fullest scope, might contain wonders that are permanently beyond the reach of human understanding, existing in a silence we can never translate. Others might look almost exactly like ours, with only tiny differences. While some universes in the multiverse might be utterly unrecognizable, others could look almost exactly like our own. The same galaxies might spiral through the same voids, the same stars might burn with the same light, and the same planets might orbit in the same patterns. The difference could be as small as a single atom in a different position, or a single photon that traveled a slightly different path. From the outside, such a universe would be indistinguishable from ours in almost every way. But that tiny difference could cascade through time, producing a history that diverges from ours in subtle and unpredictable ways. A butterfly might have landed on a different flower, a raindrop might have fallen a moment later, and the entire course of events might have shifted as a result. These near-identical universes would be the closest neighbors to our own in the vast landscape of possibility. They remind us that even the smallest change, magnified over billions of years, can lead to a reality that is both intimately familiar and quietly different from the one we know. There may be a universe where Earth has two suns instead of one. In our solar system, Earth orbits a single star, the Sun, whose steady warmth has nurtured life for billions of years. But in some other universe, or even some other corner of our own, a planet like Earth might orbit two suns instead. Binary star systems are extremely common in our galaxy, and in another reality, the conditions might have conspired to place a habitable world in orbit around a pair of them. The sky there would hold 2 points of light, sometimes close together, sometimes far apart, casting double shadows across the landscape. Sunrises and sunsets would be more complex, with days of varying brightness depending on the positions of the two stars. The climate would shift in patterns unlike anything on Earth, with seasons influenced by the gravitational dance of two stellar bodies. Life that evolved under such conditions would be adapted to rhythms entirely foreign to us, flourishing in a world where warmth comes from two sources and darkness is a rarer guest. It is a gentle reminder that the familiar single sun of our sky is only one possibility among many. In another, the moon might never have formed, leaving Earth unstable and chaotic. The moon plays a quiet but essential role in the stability of our planet. Its gravitational pull steadies Earth's axial tilt, preventing wild swings in climate that could make the surface uninhabitable. Without it, Earth's axis might wobble chaotically over millions of years, plunging regions from tropical warmth into freezing darkness and back again. In another universe, the moon might never have formed at all. Scientists believe our moon was created when a Mars-sized body collided with the early Earth, and if that collision had never happened, our planet would be a very different place. The tides would be far weaker, driven only by the distant pull of the sun. Nights would be darker, lit only by starlight. The length of our day might be different, and the rhythms of life that evolved in harmony with lunar cycles would never have existed. An Earth without its moon would be a more chaotic and unpredictable world, still beautiful perhaps, but far less stable. It is remarkable how much we owe to that gentle companion drifting quietly through our night sky. Some universes may allow stars to live for trillions of years rather than billions. In our universe, the lifespan of a star depends largely on its mass. The most massive stars burn through their fuel in just a few million years, while smaller, cooler red dwarfs can shine for trillions of years. In some other universe, the balance of fundamental forces might allow all stars, even large ones, to burn for extraordinarily long periods. If nuclear fusion were slightly more efficient, or if gravity held stellar cores together more gently, stars could endure for trillions upon trillions of years. The implications for life would be profound. Planets orbiting such long-lived stars would have unimaginably long windows in which to develop complex biology. Civilizations could rise and fall countless times, each one building on the foundations of those that came before. The slow, patient warmth of such a star would provide stability that our own sun, with its mere 10 billion-year lifespan, cannot match. In such a universe, the gentle light of ancient stars would persist long after our own cosmos has grown dark and cold, a testament to the enduring power of patience. Others might see stars burn out in mere millions of years, too fast for life to evolve. At the other extreme, some universes might have stars that burn through their fuel with terrifying speed, exhausting their nuclear reserves in mere millions of years. If the strong nuclear force was slightly more powerful, fusion reactions in stellar cores could proceed at a furious pace, converting hydrogen to helium and beyond in a fraction of the time it takes in our universe. Such stars would blaze with extraordinary brightness, but their lives would be tragically short. The heavy elements needed to build rocky planets and complex molecules would be scattered into space quickly, but there might not be enough time for those elements to gather into planets before the next generation of stars burned out. Life, which took roughly 4 billion years to develop on Earth, would have no chance to emerge in such a rush. The universe would be a fireworks display, dazzling but brief, each generation of stars flaring and fading before the chemistry of biology could even begin. It would be a cosmos of brilliant but fleeting beauty, where time itself is the missing ingredient for life. If every story imaginable plays out somewhere, then imagination itself is a map of realities. If the multiverse is truly infinite and every possible configuration of matter and energy exists somewhere, then every story ever told, every world ever imagined, and every scenario ever dreamed might correspond to an actual reality. In such a multiverse, imagination would not be merely creative, but cartographic, a way of mapping territories that genuinely exist. The fantastical worlds of fiction, the impossible landscapes of dreams, and the speculative scenarios of thought experiments would all be descriptions of real universes somewhere in the infinite tapestry. This idea blurs the boundary between fiction and reality in a deeply unsettling way. It suggests that nothing we can conceive is truly fictitious, only distant. Every nightmare, every utopia, every quiet afternoon we have ever imagined might be playing out somewhere under different stars. The human mind, in this view, is not merely a factory of invention, but a window onto the possible. As you rest tonight, the stories drifting through your thoughts might be echoes of realities unfolding far beyond the horizon of our cosmos, real and quiet and waiting. The multiverse might mean that nothing is unique, not even you. If the multiverse is infinite and every possible arrangement of matter occurs somewhere, then uniqueness itself might be an illusion. There could be countless copies of you scattered across the multiverse, each one living a life that is identical to yours in every detail. The thoughts you are thinking right now might be mirrored by an infinite number of other versions of yourself, each one equally real and equally convinced of their own individuality. The idea challenges our deepest sense of identity because we tend to believe that we are singular, that there is only one version of each person. In an infinite multiverse, that belief may not hold. Every experience you have ever had, every choice you have ever made, and every moment of consciousness you have ever felt might be replicated endlessly across reality. It is a thought that can feel disorienting, as though the ground beneath your sense of self has shifted. But it can also be oddly comforting, a reminder that you are woven into the fabric of something far larger than any single life. In the multiverse, you are not alone, not even close. Or it may mean that every universe is singular, precious, and irreplaceable. There is another way to look at the multiverse, one that finds beauty rather than insignificance in its vastness. Even if countless universes exist, each one could be singular in its own way, a unique combination of constants, laws, and histories that will never be exactly repeated. Our universe, with its particular arrangement of galaxies and stars, its precise balance of forces, and its improbable gift of life, might be genuinely one of a kind. The fact that other universes exist does not diminish the value of this one, just as the existence of other people does not diminish the value of a single life. Every universe in the multiverse might be precious precisely because it embodies a particular possibility that could exist nowhere else. The stars that shine in our sky, the planet beneath your feet, and the consciousness with which you perceive them are all expressions of this universe's unique character. Rather than making everything meaningless, the multiverse might make everything meaningful, because every reality is a singular thread in an infinite tapestry, irreplaceable and quietly extraordinary. Some physicists believe the multiverse is unavoidable given our best theories. The idea of the multiverse is not just a flight of fancy. Some of the most respected physicists and cosmologists in the world believe that the multiverse is an unavoidable consequence of our best scientific theories. Eternal inflation, one of the leading models of the early universe, naturally produces an endless array of bubble universes, each with potentially different physical constants. String theory, which attempts to unify all the forces of nature, predicts an enormous landscape of possible solutions, each corresponding to a different universe. The many worlds interpretation of quantum mechanics suggests that every quantum event branches reality into parallel paths, all of which are equally real. These are not fringe ideas, but mainstream theories pursued by serious researchers at the leading institutions of science. The multiverse emerges not because anyone wished it into existence, but because the mathematics of our most successful theories points towards it. Whether or not we can ever observe another universe directly, the theoretical case for the multiverse continues to grow stronger with each passing decade. Others believe it lies forever beyond the reach of science, in the realm of imagination. Despite the theoretical arguments, not all scientists are convinced that the multiverse belongs within the boundaries of science. Some believe that any idea which cannot in principle be tested or observed lies outside the realm of scientific inquiry, no matter how elegant its mathematics. The multiverse, by its very nature, may be forever hidden from us. If other universes exist beyond our cosmic horizon, separated by barriers that no signal can cross, then we may never gather direct evidence for or against their existence. Critics argue that this places the multiverse closer to philosophy or imagination than to empirical science. It is a fair concern, and the debate continues in lecture halls and journals around the world. But perhaps there is beauty in this uncertainty too. The multiverse sits at the very edge of what we can know, a place where science meets wonder and careful reasoning blends with quiet awe. Whether it is ultimately proven or forever remains a dream, the multiverse reminds us that reality may always hold mysteries beyond our grasp. And on quiet nights like this, that thought can be a gentle companion as you drift towards sleep. And now, the quiet wonders of the multiverse begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about parallel universes and infinite possibilities, from bubble universes drifting in a cosmic sea to branching timelines where every choice unfolds, from black holes that may be gateways to new realities to brain collisions that could birth entire worlds, from universes with no stars to those where stars burn for trillions of years. You have explored how the laws of physics might shift from one cosmos to the next, how time itself might not exist in every reality, and how life might flourish in forms we could never recognize. You have learned that our own universe, with its stars and galaxies and the delicate balance that allows for life, may be just one possibility among countless others. You are connected to this story more deeply than you may realize. Right now, as you listen, the atoms of your body were forged in the hearts of ancient stars. If the multiverse is real, those same elements may exist in parallel forms across infinite realities. Somewhere, if infinity allows, there may be other versions of you, living lives both familiar and unimaginably different. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the quiet pulse of universes drifting through an endless cosmic sea, like the silent expansion of realities we may never touch. Tonight, as you rest, the multiverse continues its quiet existence beyond our reach. It holds mysteries that may never be solved and possibilities that stretch the imagination to its limits. It suggests that our cosmos, vast as it is, may be only one thread in an infinite tapestry of realities. You are a small, warm presence within this vast expanse of possibility, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that reality may be far stranger and more beautiful than we ever imagined. That somewhere beyond the edges of everything we know, other universes may be unfolding, each with its own stories, its own stars, its own quiet moments of peace. Thank you for joining me on this journey through the mysteries of the multiverse. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the cosmos and its infinite possibilities. There are more wonders waiting, more secrets hidden in the fabric of reality and the quiet corners of existence, more gentle truths to drift through on quiet evenings. Rest well, and may the vastness of the multiverse keep you company through the night. This has been Drowsy Discovery. Good night.